not on website, it's on the internet, it's on the web. Google Purdue final exam schedule. The first link should take you to
Okay, because I was going home for Christmas, I went international,
yeah,
so I needed
just
to book
Google.
my
I
flight.
think it's on the Wednesday of that week.
Wednesday. Okay, thank you so much.
Okay, let's get started. All right, so the calendar here, reminder again, the exam next Thursday, October 19, same place, same time as last time. Okay, so it'll cover everything up to what we're doing today. We'll cover one more lesson on Friday and the next Monday, but those two lessons will not be on exam 2. Okay, so notice it says 11 through 20. 20 is what we're doing today. Second thing, people are asking me about the final exam schedule. Well, here it is. Our exam is on Wednesday, December 13, 10:30 a.m. to 12:30 in Elliott Hall. All right. By the way, you can get to this big thing right here just by simply Googling Purdue final exam schedule or Yahooing whatever thing posts up. Okay. All right, so today we're going to be looking at section 3.8. More applications on using the derivatives to solve certain problems. Okay, topic is on exponential growth or exponential decay. If we have something, a quantity of something, call that y as a function of time, y of t. If you say it is growing or decaying exponentially, then what you're saying is that if you were to graph this function right here, you get a graph of an exponential function. Exponential functions in general, if we use the variable we're using here, y of t here, it's some constant. I'll write y as at 0 for now as a constant, times some exponential function e to the power of some other constant k times t. And you'll see in a little bit what these numbers, what these constants refer to. Okay, so plain and simple, if you were to graph something that's growing or decaying exponentially, you get a graph of an exponential function. So here's an example of a graph that might be an exponential growth situation. It's going to behave like e to the something, and we know what it does. It starts low, and then gets higher and higher and higher. Exponential decay is the reverse situation. Instead of things getting bigger over time, things get smaller over time. So it'll start high, and then becomes lower and lower, approaching the horizontal asymptote that's on the t-axis right here. So this is an example of a growth situation. Here's an example of a decay situation. The y-intercept right here, this is that y of 0 thing. This is the amount of whatever this substance is, whatever that quantity is at time 0. So that's your y-intercept. Now this k right here, take a look at this equation right here. This is a constant, a number. K is also a constant. And notice what happens if I take the derivative of this function right here. If I take the derivative dy dt, the constant doesn't do anything. It sits right there. And when I take the derivative of e to the kt, I get e to the kt times k by the chain rule. Okay, e to the something derivative is e to the same thing times derivative of that power. Now notice that this quantity right here, y0 times e to the kt, that is precisely the definition of y of t. Right? Look about right here. above that line. That's the definition of y. So this is telling you that the rate of change of something that's growing or decaying exponentially is equal to some constant y, k, times y itself. We say that the rate of change is proportional to the size or the quantity of y of t. Right? Rate of change of y, how fast this thing is changing, is some constant times itself. The bigger y is, the faster the rate of change. The smaller y is, the smaller rate of change. And now you can see the rate of change, assuming y is always positive, and that's usually the case, then is determined by the sign of k. If k is positive, then dy dt is a positive number, and that's a growth, right? If k is positive, we have a growth because dy dt is greater than 0. A positive rate of change, things will get bigger over time. If k is less than 0, then you have a decay situation. You're losing quantity over time because the rate of change is negative. Okay, so two important equations to keep in mind are, of course, first, this one right here. And also that the rate of change is equal to itself. This k is often called a constant of proportionality. And then y of 0 is whatever the size of this thing is at t equal to 0 when we start to track the size of y, the quantity, the size, the overall amount of it. Okay, we all know that there are many things that can be modeled exponentially, like population, radioactive decay, carbon dating, that kind of thing. So I prepared 4 examples. We may not be able to get through all of them, but we'll see how many we can get through. Okay, does everything on this page make sense? Any question? Yeah. Here? Yeah, because remember, when you take the derivative of t is like an x over here. So when you take the derivative of e to the 2x, for example, you get e to the 2x times 2, right? Because 2 is the derivative of the exponent. And variable here is t, so k is what we get when we use chain rule. Okay? All right, so here's the first example. Many bacteria, simple organisms, they grow, our cells in our bodies grow the same way. They grow by dividing itself into 2 every so often. And a lot of bacteria do that too. They're very simple organisms. So the E. coli bacterium divides itself into 2 cells every 20 minutes. That means for every 20 minutes you wait, the number of bacteria that you're tracking will double, right? You start with 1, 20 minutes later you get 2. And those 2 again will double into 4 20 minutes later. And those 4 double into 8 another 20 minutes later, and so on. So this is growing at a rate proportional to how many there are. And therefore it's an exponential growth. Suppose the initial population of a culture is 50. We're going to find 4 things here, and we'll deal with them one at a time. Okay? All right, let me put this on the other projector. Okay, so because these things double, even though that doubling rate doesn't change, the absolute rate changes. You have 1 grows to 2 in 20 minutes, and that goes to 4 20 minutes later, and then 8, right? The more there is, the faster there will be, the faster the size will grow. So the fact that this is a situation going on tells us we have an exponential growth. So the two equations we saw on the first page are what we need to use to solve this problem. This describes the exponential growth. And remember that this is equivalent to saying that its rate of change is proportional to itself, k times y. Y is the size of that bacteria culture we are tracking. Okay, so let's solve the problem here. First part here, find the relative growth rate. And you'll see how we can work with that. The key thing with these problems is that you need to find out what y of 0 is. Usually it's given, usually. And also you need to figure out what k is equal to. If you could find out those two things, then the problem is essentially solved. It tells you everything you need to know in that equation. The problem gave me the initial size, y at time 0. We assume we start tracking this situation at time 0. And it's 50, right? The problem says so. K deals with how fast this thing is growing. And it has something to do with the doubling every 20 minutes. So we know that y of 20, if I wait 20 minutes, if I start at 50, if I wait 20 minutes, I'm going to get 100. Right? Those 50 will split into 100. And if I wait 20 more minutes, I'm going to get doubling that again, 200, and so on. So somehow I need to figure out k. Let's look at this equation again. I know y of 0. It's 50. I also know that if I wait 20 minutes, I get 100. So if I take this, plug into this equation right here, y of 20 is 100. I replace the left-hand side with 100, and I'll replace that t with a 20. Right? I know I start 50, I get 100 20 minutes later, so the same equation can be turned into that. The future amount, 100, is equal to the initial amount, that never changes, times e to the k, we don't know what it is yet, times time, 20 minutes. The only thing I don't know in this equation is k. So that's easy to solve. Let's divide it by 50. That's a 2, of course. Take the natural log on both sides. And we know we can move the 20k. Ln of e to the something is simply that something. So there we go. Simple property later, we get 20k is equal to ln of 2. And this tells us that k is equal to 1 over 20 times ln of 2. Or ln of 2 to the power of 1 over 20. And if you have a calculator, you can actually calculate what this is. It turns out to be about roughly 0.035. Okay? Questions so far? Yeah. Why do I use minutes? I could use any unit if I want. If I wanted to use hours, then this would be 1 over 3 instead of 20. It's my choice, and I chose 20 because that's what the problem started with. I chose minutes because that's what's given here. I could use seconds if I wanted to. It's a choice. Make a good choice. Other questions? All right, good. Now let's move on. Now we know k, right? Our equation looks like this. Y of t is equal to the initial amount times e to the k, right here, times t. This is our k, remember? Right here. Notice that the stuff in the green set of parentheses I just drew is e to the ln of something. So this really reduces to 2 to the power of 1 over 20, still raised to the power of t, or 50 times 2 to the power of t over 20. We'll come back to this equation. We'll need this for parts B through D. Okay, now let's look at the rate of change. This is equivalent to dy dt is equal to k times y. Or this time it's more useful to use 0.035 as my k. And this equation says the rate of change of my number of bacteria is 0.035 times the present number of bacteria. This thing right here, this is what's called the relative growth rate. $0.035 is equivalent to 3.5%, right? That is our relative growth rate. At any given time, the rate of change of the number of bacteria in this culture is 3.5% times the size it has. So it's 3.5% times initially 50, whatever number that is, that's the initial growth rate. The more there is, the faster this overall number will be. But it is always maintained at 3.5% relative to what I have. This is like the interest rate on your credit card or savings account. It's always the same relative rate to the account balance. But of course, the more there is, the faster the credit card balance grows or the amount in the savings account grows. So this K here, we also see is equal to the growth, the relative growth or relative decay rate of the situation. Okay, so part A, we found out the situation here, 3.5 times whatever the present size is equal to. Question on this page. Are we good to move on? Yes? Nod your head if yes, so I can see. Good, good, good. Okay. All right, so revisit the problem statement. Part B, what do we want? We want to find the number of cells after 6 hours. Well, that's simple now. If you have the equation at the lower left corner of the last page, part B is trivial. From A, we found that y of t is equal to 50 times 2 to the power of t over 20. Here, remember to keep in mind that t is in minutes. We started with minutes, we stick with minutes. Whatever choice you made in the beginning is what we stick with. That choice is yours, but you got to stay consistent. 6 hours later, 6 hours in minutes is 6 times 60, 360, right? So the number is equal to y of 360 equal to 50 times 2 to the power of 360 over 20. That's 50 times 2 to the power of, that's 18. This tells you it goes through the doubling time 18 times. It doubles 18 times. That much time later, it doubles 18 times. That 2 tells you doubling. So this part you need a calculator, of course. Rounding to the nearest whole number here, 13,107,200. You start with 50, you wait 6 hours later, you get 13 million. You wait another 6 hours, you get another huge amount. All right? So B is easy. We did most of the work in A already. Part C, rate of growth. This is the absolute rate of growth now. That's the right-hand side of the rate of change equation. K by itself is the relative growth rate. If you multiply that by the size at that time, that's the absolute growth rate. It's always 3.5% relative to the size, but what is the actual absolute size, rate of growth? And this is also pretty simple. You simply plug in the y, k we found earlier, and this y from part B. dy dt is equal to k. K is roughly 0.035, right? And y from this part above, 13,107,200. It's relative to this number, so it's 3.5% of that number. This turns out to be, again, rounding to the nearest whole number here, is 454,260. And that would give, the units would be bacteria, the number of bacteria per minute. Every minute you wait at that instant right here gives you about 500,000 more at that present time. It maintains at 3.5%, but because of this number keeps getting bigger, this number also will be getting bigger as time goes on. Last part, when will this population reach 1 billion? Well, that's again, if you have the equation, this one right here, finding out when the population reaches 1 billion is pretty easy. You want y, the future amount, to be 1 billion. That's a lot of zeros. right? You want y to be this number, and you're asking yourself, what is the t that's going to give me that number of y? Plug it in. 1 with 9 zeros equal to 50 times 2 to the power of t over 20 divided by 50, and I get 2 with 1, 2, 3, 4, 7 zeros after that. What's that? 7. 1, 2, 3, 4, 5, 6, 7. Yeah. It's whatever this divided by 50 is. It's that number. Okay, let's solve for t. Let's take the natural log. Natural log of this thing equal to, take the natural log, we bring the t over 20 out to the front, natural log of 2. So t turns out to be 20 times natural log of that number. 1, 2, 3, one more. Divided by natural log of 2. Turns out to be 485. And that would be in minutes. I found my k using minutes as my unit of time. So when I solve for time here, I'm going to get minutes out of it, which is roughly, very roughly 8 hours. Okay, so we start with 50. 6 hours later, 13 million. You wait 2 more hours beyond that, you get 1 billion. You wait another 2 more hours, who knows what this number will be. We know it's going to be very much larger than 1 billion. Right? And this is assuming that nothing is stopping this thing from growing. If you don't want this situation to happen, what would you do? You would use some kind of antibiotics, for example. That will stop the rate of growth. But left uninhibited, this is kind of situation that can happen. All right, let's do another one dealing with population here. The table below gives the population in millions. So 83 doesn't mean the population is 83. It means 83 million of a certain country in the second half of the 20th century. 1950, 83 million. 1960, 100 million. 1970, 122, and so on. And 2000 is 214 million. So these are the actual figures. Now suppose you are running that country, and at the end of the 1960 decade, you want to project what the population would be in 1980. If you didn't have these numbers here at the time, of course you wouldn't. Using the exponential growth model, what would you project the population to be in 1980? And that's the problem we're trying to solve here. Once again, we're dealing with an exponential growth problem. Population works. The more people there are, the faster the population will grow, right? So we're dealing with exponential growth because the rate of growth is proportional to the number of people at that given time. So here's our key equation. And as usual, we're going to need to find out y of 0 and then the number k. Once we know that, everything is contained in that one equation. Here, instead of using these big numbers for years, let's just declare 1950 as our t equal to 0. We'll let year 1950 be t is equal to 0. And let's measure t in years. It's a choice you have to make. The last one, I made a choice to use minutes. I could have used hours. I could have used seconds if I wanted to. Here, I'm going to measure t in years. I could do decades if I wanted to. But again, stick with something and then stay consistent with that unit. So that means y, the population at t equal to 0, 1950, is 83 million. And if I wait 10 years later, 1960, population is 100 million. Right? The table tells me 1960, t equal to 10. 10 years after when I start, I have 100 million people. So here we're going to use this to build an exponential growth model. That's just a really, really fancy way to say find k. And we'll use that to project population in 1980, which means y at 30. Right? 1980 is 30 years after 1950. If 1950 is 0, then 30 years later, 1980, that would be y of 30. All right, so here's the equation. So this guy, y of t is equal to initial population, 83, e to the kt. And then we'll take this piece of information. It tells me that y of 10, if I change t to a 10, my y turns into 100. And the only thing now we don't know in this equation is k. And we know how to solve this. Divided by 83, take the natural log, and we can find our k after that. Equal to. So natural log of 100 over 83 is 10k, which gives us a k of 1 over 10, natural log of 100 over 83, which turns out to be about 0.0186. Okay, just like in the last problem, this k, remember, tells us the relative rate of change, relative growth rate. So in this example, this tells us that the relative growth rate is 1.86% of population. It's relative to be about 1.6% of the population you've got. The more there is, the faster the absolute growth rate. But the relative growth rate, just like the interest rate, is kept fixed, 1.86% of whatever the thing is multiplied to. Okay, now we can project what's going to happen in 1980. Y, that's 30 years later, using this equation right here. 83 times e to the k. So in the last example, I did something different with the k, and the equation turned out to be different. It's entirely equivalent to simply using that number of k. It's just a preference, really. 83 e to the k times t, 30 years. And this turns out to be 145. Of course, measured in millions. Okay, exponential growth projects 145 million. The actual number from the table, 150. So it's pretty close. It's pretty close. And that's not always going to be the case. Because remember, in exponential growth, we're ignoring the fact that the population could decrease. Our model doesn't say anything about a decrease in population due to age, due to disease, due to other kinds of factors. It also doesn't take into account the environmental cap. We know that the Earth can only sustain a maximum number of life on this planet. Eventually, resources run out, water runs out, food runs out. That doesn't get taken into account in exponential growth. But for short duration, usually it's not too bad. You wouldn't use exponential growth to project what happens 3 centuries later. That's not going to be accurate, not even close. But 30 years, that's not too bad. That's usually not going to be too bad. Okay, like in this example, the difference was only 5 million. Questions? Okay, let's do one more example. We probably won't get to the fourth one. So what I'm going to do is finish the third example here, and then I'll finish the fourth example before I upload the notes. So look at the notes after class. Example 3, this is an exponential decay kind of thing. I'm sure many of you are familiar with the concept of carbon dating. Okay, the radioactive isotope of carbon, carbon-14, has a half-life of 55,730 years. Half-life means the amount of time you have to wait before half of your initial amount decays to something else. Essentially, it's time to lose half of the initial. It's the opposite of the 20-minute doubling time in the bacteria problem we did. It's analogous to that, but it's the opposite. It takes 20 minutes to double the amount of bacteria. Here, this thing naturally decays to something else. So time to lose that is almost 6,000 years. By comparing the amount of carbon-14 in an ancient sample and a similar modern specimen, such as a plant or animal, the age of that ancient object can be approximated. So what happens is that cosmic rays from space bombards the atmosphere and and produces carbon-14. So when we breathe, when we eat things, we are absorbing carbon-14. And so in our body, we have carbon-14 level. That's about the same as what's in the atmosphere. But when we die, we obviously no longer exchange that, right? So if you look at an ancient object, that carbon-14 stays in that ancient object and decays over time at this rate. If you compare that ancient object, if you measure the amount of carbon-14 in that ancient object compared to a modern similar thing, you can roughly find out how old that thing is, because we know precisely how fast carbon-14 will decay. And that's basically how people approximate the age of an ancient bone, an ancient book, for example. Bones are pretty easy. You find an ancient human bone, you know the modern human is going to have this amount of carbon-14. How much is in that bone? That's roughly the age. We can back it out. All right, so anyway, how old is an object that has about 33% as much carbon-14 radioactivity as does its modern-day counterpart? Okay, let's figure that out. Before we even do any math, is the number we are expecting bigger or smaller than the half-life? Yeah, we lost more than half, right? If we keep 33, we lost 67. That's more than half. It takes about this much time to lose half. We are expecting a number bigger than 5730. If you got a number smaller than that, you're wrong, right? You're wrong. So let's figure that out. It's good to do stuff like that, you know. Know what you're expecting, and when you get it, see if that makes sense. So there's our key equation. In this example right here, this initial amount really is not that important, and you'll see why. If I know the half-life is 5730 years, that means if I wait that much time, my future amount, y of t, is going to be half of whatever I started with. Right? No one ever told me how much I started with, but I know that no matter how much I started with, if I wait this many years, I will have half of whatever I have. And notice that this means that the initial amount really doesn't matter. In other words, the half-life tells us that time to lose half is independent of the initial amount. It's the same amount of time. Just like the population is going to double every 20 minutes regardless of how many you got. You start with 1, 20 minutes later you get 2. But if you start with 1 billion, 20 minutes later you get 2 billion, right? The doubling time doesn't change, independent of what you got. Exactly the same as the bacteria. Okay, so here I can find k very quickly because the y0 doesn't matter. Take the natural log. Natural log of e to the something is just something. So k is equal to 1 over 5730 ln of 1/2, which is negative 0.000121. Negative k, we're losing something. The rate of change is negative. We're losing something. So that's the relative rate of decay. So this tells us that we lose 0.000121 is 0.012% per year. And every radioactive isotope has different half-life. Certain things have very short half-life. I think radium radium, that's right, radium has half-life that's like, I think 10 days or so. And this thing has a half-life that's 5730. Certain things have half-life that are fractions of a second. They're very unstable stuff. Okay, so anyway, that's our k. So our t equation, of course, is then y0 e to the k 0, 0, 0, 1, 2, 1 t. And we're told that the ancient sample has 33% of carbon-14 compared to modern day sample. This could be an ancient human bone, for example. You just find out how much is in your body, and that thing has 33%. We know exactly what to do. This tells us that y of t is 33% of whatever we started with. And we're looking for what t in that equation can make this happen. 33% of what you started with. Okay, plug this into here. And once again, that y0 doesn't matter. If y0 matters, then carbon dating is not going to work because it depends on the size of that object now, right? So your finger, a bone in your finger versus your leg bone, that's going to give you a different number. But the fact that it doesn't matter what the initial amount is means that the carbon dating is going to give us some pretty good approximation. Okay, let's figure this number. So let's take natural log. Solving for t. And notice all of these things really need calculator. On the exam, we'll give you stuff that you don't need to use a calculator. So if this were to be on the exam, then the choices will have just natural log of something that you don't have to calculate. This turns out to be 9165 years. Okay, it's bigger than our half-life because we lost more than half. Okay, let me show you example 4 before. We're not going to have time to do that in class, but it's a pretty neat example, and I'll just show you. And too bad, it's kind of an interesting one. You have to wait for my solution. I'll write it up. Takes me maybe 10, 15 minutes to write it up. So you found this body, and you measure the temperature, and now you're trying to figure out when the death occurred. Knowing our normal body temperature and the environmental temperature. A little bit of CSI here. So I'll write out the solution before I upload the notes, and it's a pretty interesting example. That's it. See you Friday. Right.